All right. Welcome back. Thank you for coming back. All right. So for this second lecture out of 4, we'll go through hyperarithmetic sets, and I think we'll start. I don't think we'll get to the end of part 3. So maybe I'll get to the best. Well, we'll see what we get. But yeah, it's a nice continuation of that one. And I guess we'll start next time with the end of this one and the rest. Okay, so hyperarithmetic sets. So before we start with hyperarithmetic sets, let's quickly review what arithmetic sets are. So we have, I said this already, I guess, but I'm going to write it down so we can do the parallelism. We have the vocabulary of number theory, 0, 1, plus, times, less than or equals, and we are talking about numbers. A set A is said to be arithmetic if it's definable in the natural numbers by a first-order formula in the language of arithmetic. The set of all n's which satisfy the formula. That's an arithmetic set. Definable in arithmetic. And I guess being arithmetic is equivalent to being computable in the nth Turing jump, the nth iterate of the Turing jump from some natural number n. It's also equivalent to, and I guess I won't prove it, it's many one reducible to one of these sets from the previous part, the set of all indices of well-orderings less than or equal omega to the n for a natural number n. These are all arithmetic, and being arithmetic is the same thing as being many one below one of those guys. I guess you can see that that's because I'm going to generalize that. Okay, so those are arithmetic sets. So now let's go to hyperarithmetic sets. I guess I'm going to take a path that is not the standard one. So at least you'll see a different way to reach the hyperarithmetic sets than the usual one. And the path is through infinitary formulas. It is, so first, so the previous definition here was the standard first-order formulas. Now we are going to consider infinitary formulas. So they are still first-order formulas because first-order just means that for all and there exists the range over elements of the structure, in this case natural numbers, but not over subset of the structures, that will be second order. So first order means for all and exists range over elements of the structure. Infinitary means that the conjunctions and disjunctions, so the ands and the ors, can be over an infinite set of formulas. You can take an and of infinitely many formulas or an or of infinitely many formulas. So that's the language that is usually denoted by L omega 1 omega. And here the omega 1 means that the conjunctions or disjunctions have to be size less than omega 1, meaning countable. And the omega means that there's for alls and the number of free variables and the number of strings of quantifiers has to be less than omega, namely finite. So L omega omega is standard finitary. This is for the disjunction, this is for the for alls. So here, just 2 examples, if you haven't seen these formulas before. So if you have a group, for instance, you can say that an element is torsion by this formula. It's an infinitary disjunction. This big O, this is a big O. Infinitary disjunction of this formula. Some x multiplied with itself n times has to be an entity. That's what it means for x to be torsion. If you want to say that x is divisible means that it's divisible by every natural number. You have to say that for every natural, it's a conjunction over all the natural numbers. There exists a y such that y multiplied by itself n plus 1 times is x. So these are infinitary formulas in the language of the group, E and star. So the or and the and, they are kind of like a exist or for all, right? Except that this exists here is over n in the natural numbers, and here we're talking about this structure, the structure of groups. So we don't want to do exist in the natural numbers. We're only talking about the structure inside this particular language. So that's why we need to write at this junction. It wouldn't be part of the language. This n here is not part of the language. This n is here is just telling you what the formula is. So neither of these two relations can be defined by finitary formulas. They need infinitary formulas to define them. They're not first order definable, but they are infinitary definable. Okay, I'm not going to use this in the rest of the talk, but just to tell you the two kind of main properties of this language. One, these are due to Dana Scott from 1965. If you have a countable structure A, it's a countable structure in some vocabulary, there is an infinitary sentence, so without free variables, such that identifies the structure uniquely among all countable structures. So this sentence is true about A and is only true about things that are isomorphic to A. So it's true about C if and only if C is isomorphic to A. So it's a sentence that determines completely the isomorphism type of A. It's only true about things that are isomorphic to A. And another one, I guess, also follows from the same paper. If you have your structure A and you have a subset, a set of tuples, a set of k tuples in the structure that is automorphism invariant, then there is an infinitary formula with k variables, free variables, which defines this set within A, the set of all the things that satisfy the things. So everything that is automorphism invariant is definable in this infinitary language. So it's quite powerful, this infinitary language. Again, I went kind of quick because we're not going to use these two things. But so for countable structures, they are quite powerful. I mean, these formulas, they still get to be quite complicated, and the complexity of them tells you something about the relations and about A. So it's still not trivial. Okay, so infinitary languages, we're not going to use. Okay, so before we're going to count the complexity of infinitary language the same way as we do for the finitary, like the sigma 0 n formulas and the pi n formulas. In the case of finitary formulas, we count alternations of quantifiers. In this case, we're going to count alternations of exist and infinitary ors on one side versus for alls and infinitary ands on the other side. So we count alternations of when you go from one to the other. So for instance, a sigma n formula infinitary, the in is for infinitary, is of the form infinitary disjunction of there exist, conjunction of for all. So we are grouping these together, n alternations. And then something that has is finitary and has no quantifiers at the end. All right, so essentially the infinitary ors counts as exist, infinitary ands counts as for all when you're counting complexity. Infinitary formulas, so the complexity might not stop at defining natural numbers, because now you can have disjunction of a formula that is sigma 1 and another one that is sigma 2 and another one sigma 3, sigma 4, and you do the conjunction of L and you get something that is pi, I guess, omega, because it's bigger than all the other ones. So the complexity can go through the ordinals. And okay, before I said that here, a pi n formula, I don't know if you noticed that trick. Isn't that cute? A pi n formula, that's the definition. It just starts with and for all. In general, sigma alpha formula, if it's one of the four infinitary disjunctions that exist to y, and then the formulas that come here are pi beta for some beta less than alpha. All right, so you have infinitely many formulas there, and they are smaller pi alpha rank. And pay attention to this: pi beta formulas conjunction of sigma gamma for gamma less than beta. All right, so that's how you count alternations and quantifiers in the case of infinitary formulas. You need ordinals now. And we're going to consider the case of computable infinitary formulas that were introduced by Ash in the 90s, 80s. So an infinitary formula is computable if, what do you think? If it's computable, if you can represent it, you can write it as a computable formula. So you can choose kind of your own definition here. I mean, every formula, a finitary formula, you can write it as a tree, essentially. You have an OR, and the OR is an OR of two things. Then you have an AND, and it's an AND of two things, and for all, and then you kind of do a diagram to represent the formula. In the case of infinitary formula, it's the same. But now your tree is infinitely branching. Every time you have an OR, it branches into infinitely many things, and then have an AND, it branches into infinitely many things. So you can kind of find a way of finding an object that represents this formula. Kind of essentially, we are writing down the whole formula. But now it's an infinite tree. It's still well-founded, this tree, but it's an infinite tree. Well, so if you can represent it with a computable tree, then you say that the formula is computable. An equivalent definition is to say that every time you do a conjunction or a disjunction, you have to do it over a computable list of formulas. So if you're going to do an infinitary conjunction, you have to be able to list all the formulas you're conjuncting computably. That definition, if you want to do it formally, you have to be careful because you have to define indices. So it's a computable list of what? Of indices for formulas. Of what formulas? Of computable infinitary formulas. So it's a bit circular. So you need to do it the right way, but you can do it the right way. And so essentially, those two are equivalent. You can show that two are equivalent. Okay, so these are computable infinitary formulas. Example, the same two. So I guess, so the Julian Knight likes to say that the computable infinitary formulas are the ones that when you write ... you know what it means. Because you have a computable way of figuring out what the ... is, essentially, in your formula. Okay, so pretty much every formula you can write is going to be computable. I'm going to use this notation, LC omega, to denote the computable infinitary formula. So this means the conjunction and disjunctions have to be computable. Okay, so those two examples are very simple. Let me tell you two more interesting examples of computable infinitary formulas. These ones become quite handy. So given an ordinal alpha, this is a computable ordinal alpha, I guess. There is a formula psi alpha that says on a partial ordering P that an element has rank less than alpha. Okay, rank like the well-founded rank. And the formula is 2 alpha plus 1, the C is for computable. So pi 2 alpha plus 1, the C is computable. So it's a formula that says that the rank of this element is less than or equal alpha. So what is the formula? The formula is built by transfinite recursion. So you start from, for alpha equals 0, you say, well, there's nothing below, like there's nothing below you. And then in general, having rank less than or equal to alpha is the same thing as saying every element below you has some rank that is gamma for some gamma below you. I guess this beta and this alpha should be the same thing. So this beta here is alpha. So what this is saying is for every element below you, there is some ordinal below alpha, such that that element has rank below alpha. And we are using that. We already know how to define the psi gammas for gammas below alpha to define psi alpha. So the definition is by recursion. And then by transfinite induction, you can show that the complexity is that one up there. So you're using here two alternations of quantifier on top of the previous one. So you have for all, and then infinitary disjunction, that's can exist. So alternation, and then this one is for all. So you're adding 2 every time. That's why the 2 alpha over there. In the limit cases, you get that this one is a plus. You get a plus 1 from this for all. So if alpha is omega, this one is going to be these are all pi n for n less than omega. This one here is sigma omega. This one is pi omega plus 1. So at the limit cases, you get a plus 1, and then you add 2 every time. Yeah, so not that 2 times alpha in the ordinals means alpha repeated, 2 repeated alpha times, so 2 times omega is equal to omega. So when alpha is omega, here it just means omega plus 1. Okay, so, but this is in the case of a partial ordering. If you had a linear ordering, I'm not going to use it, but it's going to show up more or less. If you have a linear ordering, you can find this a much better sentence than that one. So that one is not optimal. This formula up here is optimal to tell the rank on an element in a partial ordering, so that can be proved. In the case of a linear ordering, there are better formulas. So in this case, you can write a formula phi sub omega to the alpha that says that a linear ordering is less than or equal omega to the alpha, and the complexity of this one is 2 alpha plus 1. Right? So with complexity 2 alpha plus 1, you can tell ranks or up to omega to the alpha. Yeah, essentially what's going on is like, well, if you want to say that a linear ordering is finite, like you don't need a sigma omega formula. You just need to say it's a sigma 2 formula. Finite is sigma 2. You just need 2 to say finite. If you want to say that it's below omega square, so it's finitely many copies of omega, you just need 2 more quantifiers over that. So for omega square, you need, I don't know, I guess it's sigma 4 or something, sigma 3, or sigma 5, something like that. So every time you go by a power of multiply by omega, you just go up 2 more levels. You have to be able to say there is a finitely many, every time you partition into finitely many things, each block, one of the blocks has to be less than omega to the previous one. So in the case of linear ordering, there is a better way of defining rank than that one. Okay, I don't want to go into details for that. So here you can see how these formulas now, they have like a much higher rank than the ones we had before. So these ones have pretty high ranks. Okay, so here's the definition of hyperarithmetic sets, which I say is not usually. I think this is probably the definition. The first one that this thought of hyperarithmetic set must have thought of. Except that it didn't, because Ash was the one who defined computable infinitary formulas in the 90s. So I say that a set is hyperarithmetic if it's definable by an infinitary computable formula in the natural numbers. Okay, so it's all the sense that satisfies some formula, but now phi is allowed to be infinitary computable. All right, so arithmetic was the first of the formula. Hyperarithmetic is infinitary computable formula. Okay, so those are the hyperarithmetic sets. So they, in particular, they contain, it's a much larger class than the arithmetic sets. Here is an equivalent definition. So you have that a set is definable by a computable infinitary formula if and only if there is a computable list of computable infinitary formulas, but over the empty vocabulary. And it's not really empty. I am allowing like a top and a bottom, like something that is always true and something that is always false, like 0 equals 0 and 0 equals 1, this, if you want, as 2 sentences that you're allowed to use. But I'm not using any arithmetic at all. These are formulas that all they have is top and bottom, infinitary disjunctions, infinitary conjunctions. They don't even have for alls and there exists, because they have no variables, because you're not using any sums or multiplications and stuff. They just have infinitary conjunctions, infinitary disjunctions, tops and bottoms, which define this set. And now I'm not even putting in which structure these formulas are true, because these are, I'm not using anything. It's just, it's a formulas over the empty vocabulary. So the proof of this from like the upward direction It's very easy, because if you have a formula in the empty vocabulary, you can easily make it into one about the natural numbers. Well, it is essentially, it can be about anything. I guess the only thing you have to say is put them all together. You have all these phi sub n formulas, you have to put them together into one. Yeah? No? It's the computable infinitary formulas. Yeah. So the same as this one. They are They are the same as this one, except that this one is in the language of arithmetic, and this one is in the empty language. Okay? So the up to right direction is the easy one. The hard direction is to transform a formula of arithmetic into one that has no empty vocabulary. But then the proof of that is not that hard, because so what you have to do is start by every time you have a quantifier of the form for every n, you change it for, so let's say, for every x, phi of x. Every time you see this inside your formula, you replace that by a disjunction over all n the natural number. Conjunction. Of phi of an n, and here you put the constant n, 1 plus 1 n times, I don't know, the constant for n. Every time you see there exists an x, you replace it by a disjunction over x. So this way you cannot get rid of all the free variables. And then your atomic formulas at the end are going to be of the form n, but this is the constant n plus m equals k, or n times m equals k, or n less than. They're not going to be, like your atomic formulas are going to have, you're not going to have variables, they don't have constant numbers. And then these ones is either true or false. So you can replace whatever your atomic formulas are by true or false, and you get rid of all the variables. So you end up with a formula with no variables. And I guess, and you have your free variable x from the beginning, you have to replace it for the appropriate constant. There is not much to that. Okay, so that's another way of defining hyperarithmetic sets. It can be defined actually with computable infinitary formulas in the over the empty vocabulary. You need the list has to be computable. Okay, so these are the hyperarithmetic sets. Yeah, okay, so I brushed that one under the rug. So I guess when you're going up, when you're going down, you started with a formula psi of y. And then, so you're going to do this transformation, and you're going to end up with, well, the first thing you do is do kind of psi n is psi of the constant n for each n. And then you transform this one using that into psi star of the variable. So you started with, with one with a variable, and then you replace it. And then I guess when you go up, you have these formulas, this list of formulas phi sub n, and then you're going to end up with a formula that says psi of x is going to say disjunction or conjunction over n in the natural numbers of x equals n implies phi of n. Now has variable x, and you put them together. All right, so those are the hyperarithmetic sets. And I guess the main property of hyperarithmetic sets is that they are the same as the delta 1, 1 sets. Let's see why. Okay, so first, if you're given a structure M and an infinitary formula phi, deciding whether phi is true in M is not as easy as it is in first order arithmetic. You have to, but it's at least sigma 1, 1. So you have to look at the formality of what it means to be true. It means the obvious thing. But one way of saying it is you have to say there exists a truth assignment for all the subformulas and all the possible assignments of the variables, the free variables in the subformulas, which is valid in the sense satisfies the rules of logic and makes the formula true. And the truth assignment here is now it's a real because it's assigning a true or false. They have infinitary subformulas. You have to assign them true or false. So this is a sigma 1, formula. Okay, so truth, deciding truth is sigma 1. And it's also pi 1 because if the formula is true, the negation is false. So the deciding the negation is also sigma 1. So all hyperarithmetic sets are delta 1 because in that case, you had to decide whether a formula is true in the natural numbers. That's sigma 1. The complement is also sigma 1. So the sets, the hyperarithmetic sets, which are definable by these formulas, are delta 1. Also, I guess this follows from. No, this is a different thing. If you're given a computable list of computable structures. So you have a lot of structures, a list of structures, M sub e, and you have one computable infinitary sentence. Then deciding for which structure this sentence is true is hyperarithmetic. Why is that? Well, each of these M's is a computable structure. So it's given to you as the domain, a subset of the natural numbers, and you have computable operations to tell the relations inside the structure M. Right? So you can replace this phi in the formula phi. Every time a relation shows up about M sub e, you can put the computable operator that tells you whether the formula is true or not. So you can translate whether this is true in M sub n about some formula being true in the natural numbers, because you're looking at the particular presentation of M sub n with domain the natural numbers. Right? So you can translate this into a computable infinitary formula being true about the natural numbers, and that's exactly what hyperarithmetic sets are. Yeah? Well, from the definition, Yes. So all these structures on the same language, let's say, yes, and it's a computable list of computable structures. Yes. So you have a computable uniform list of computable structures, all in the same language. So then the transformation, asking whether it's true in the natural numbers, is the same, and you get that hyperarithmetic. So in particular, this set, O less than or equal alpha, is hyperarithmetic, because I don't know if you remember, this is a set of indices of linear ordering such that L sub e, so E belongs to O less than or equal alpha if L sub e is less than or equal alpha. And then we had a formula that said that a linear ordering is less than or equal alpha. I don't know what I call it, phi sub alpha. There is a computable infinitary formula that tells you that this one is less than or equal alpha, that we wrote from before. So this one belongs to here if and only if L sub e satisfies this fixed formula. So by the previous one, that's hyperarithmetic. Right? So here we get the equivalence of hyperarithmetic and delta 1. So for every set of natural numbers, the following are equivalent. A is hyperarithmetic according to the definition that I gave before of being definable by a computable infinitary formula. A is delta 1, and that follows with hyperarithmetic sets at delta 1, so that's this implication. And that's the same as being many 1 below O less than or equal alpha. So we had this equivalence in the previous lecture, and this one implies that one because of corollary right here. So all of these guys are hyperarithmetic, so therefore this A has hyperarithmetic too. All right? So that's how we get that hyperarithmetic is the same as delta 1. So sigma 1 bounding was used in this proof in the middle. All right, any questions? Cool, so that's our hyperarithmetic set. The usual definition, or the old definition of the hyperarithmetic set is using iterations of the Turing jump. So let's look at that one. So now we're going to iterate the Turing jumps, not just finding numbers, but through the ordinals. And I'm going to do it as follows. So suppose we have L is a well-ordering with domain subset of the natural numbers. A jump hierarchy over L, or maybe over is better than on, is a set. So if we have L, it's going to be here, but it's here we have the natural numbers. So H is a set, a subset of L times L, such that the Lth column, so this one is H, the Lth column is the same is you take all the previous columns and take the jump. So this column is the jump of all the previous one together. Okay, so you're going as you're going up in L, each column is a jump of all the previous one together. So that's how we're iterating the jump along L. All right? So that's the notation. This means the Lth column, and this means all the previous one, the columns before L together. So you get that for every well ordering, there is a jump hierarchy on L, and it's unique. Well, because you just define it by defining recursion. There's only way of defining each column as a jump of the previous ones. And you get the usual jump hierarchy. Now, if L has size alpha, this is the alpha iterate of the Turing jump. If L has size n, this is the nth iterate of the Turing jump. So if L was omega, the first column is going to be, I guess, the jump of 0. Second column is the jump of that, so 0 double, 0 triple. So each column, the nth column is going to be equivalent to 0 to the n. It's the jump of all the previous one together. So at the end, you get 0 to the omega. Well, so if L is omega, what you're going to get here is 0 to the omega. And then if L was like omega plus 1, like in the position omega, in that column you're going to get 0 to the omega jump. But for L omega you get, yeah. There is no column equal to 0 to omega, that's right. You have to take, so if you take all the things below 0 to the omega, yeah, so in general, you will get that H up to less than alpha. So if alpha belongs to the linear ordering, this one is the one that is 0 to the alpha. All the previous ones. Yeah, you get a set of all of Turing degree 0 to the omega is there. Okay, so that's the jump hierarchy. That's how you. So one thing about these jump hierarchies is that they depend a lot on what is the presentation of your linear ordering. The linear ordering is being presented as a subset of the natural numbers, and here you're taking all the previous one, but it's not as pretty as I draw here because L is more complicated. So the previous columns are scattered around, and you're taking those, taking the jump. So as I said, what's the jump? It depends on your representation. And if you have like two well orderings, I don't know, omega to omega, two representations of a well ordering, there might be very, very different in the sense that there might be no computable way of telling how is that they are isomorphic. Usually telling that two well orderings are isomorphic requires like a lot of of jumps. Usually alpha jumps to tell that two presentations of alpha are isomorphic. So it's not clear at all that if you have two different presentations, you're going to get similar sets. Well, you're going to get different sets for sure. What you get, luckily, and that's all I can say, I guess. It's not I mean, I can prove that you get the same one, but it's not obvious that you will. So I guess, fortunately, we get the same Turing degree. So if alpha and beta are different presentations of the same ordinal, but maybe these are very different, it's very difficult to find the isomorphism, then, and you have jump hierarchies on them, then they are Turing equivalent. And the reason is that even though alpha and beta might be very hard to compute, how to go from alpha to beta, you can compute an isomorphism from alpha to beta that is computable in H to the alpha. And actually, you have to be much more careful than that when you do the proof, because you have to do it by recursion. So at each step, you have to use that many ordinals to compute the isomorphism up to that step and make sure you're keeping the isomorphism to make it work. So that proof, I mean, it's a little subtle, and it just works. So usually, the isomorphism from alpha to beta needs a bit less than H to the alpha. For example, 2 copies of omega. To find an isomorphism, you just need 0 jump. You don't need 0 to the omega. But it gets, in some ordinals, it gets very close to needing actually H alpha. So now we can, so since these are the same up to Turing degree, we can define a Turing degree 0 to the alpha just from the ordinal alpha, because it's independent of the presentation, if you do it up to Turing degree. If alpha, I was thinking of this, I don't know the answer. If alpha is a successor, the previous ones are Turing equivalent, so the next ones are many 1 equivalent. So actually you get a many 1 degree that is the natural 0 to the alpha. If alpha is a limit, this proof doesn't tell you these two are many 1 equivalent. There is if you have a nice presentation of alpha, there is a nice many 1 degree. But if it's an alpha that doesn't have nice presentations, right? Okay. But for omega, for instance, there is a natural many 1 degree that is the one. For other ones.
So actually, Adam showed also that you don't even get big
So with our result with Takayuki is that if you have a super nice presentation of alpha, then you have a many 1 degree that is the natural one. But you need to know a lot about that presentation. And what is that? Do we know what that is? How much is that you need to know to have the natural many 1 degree? Well. Uh-huh. Okay, so at least you get a Turing degree. And that's an interesting question. Okay, this is, I'm going to prove this, but the connection with what we had before, this O less than or equal omega to the n has the same Turing degree as 0, as the 2nth jump of 0, and for ordinals beyond, like infinite ordinals, you need the +1 over there. And this has to do with those formulas that I told you about, the formula that being an ordinal less than or equal omega to the alpha is of whatever complexity. You have to show that those are sharp, essentially.
I remember corresponding with Montalban, and he told me that people back in the day were made they didn't
Of this theorem. Yeah. Yes, yeah. Okay, so that. Yeah, so that's what I meant when I say luckily, because I feel it's like, fortunately it's true, but it's not obvious to me. I don't have an argument that it's like, of course it has to be true. No, you have to go through the proof and see it. So yeah, it's nice that it's true, but yeah, it had to be, the proof is a bit delicate when you have to look at these isomorphisms level by level. Okay, so this just tells you that. So before we had that being hyperarithmetic is the same as being many 1 reducible to one of these guys. Well, now we have it's also equivalent to being many one reducible to one of the iterates of the jump, because these guys are exactly the iterates of the jump. If you put a less than or equal here, you get the intermediate step between, because these are going by two jumps. If you want the intermediate, you put a less than or equal. So you get all the jumps. All right. So let's start with part 3. And I think we won't finish. Okay, so this one now we move to, we move from the 60s to the 2000s. Well, okay, the first one is from the 50s. Also Spector's theorem. It says, well, okay, it says that. Before that, every hyperarithmetic well-ordering, so if you have a well-ordering that has a hyperarithmetic representation, it's also computable. Hyperarithmetic well-ordering must be computable. So that's another way of, a formal way of saying that if you have a hyperarithmetic well-ordering with domain omega, then that's isomorphic to a computable well-ordering. You can build a computable well-ordering that's isomorphic to it. So that's what I meant by when hyperarithmetic is recursive, because you go from hyperarithmetic isomorphism. If you have a hyperarithmetic one, you have a recursive one. The proof of this is sigma 1 bounding. Consider all the indices of linear orderings which embed into this particular linear ordering. This linear ordering is hyperarithmetic. And so you can see that this set is sigma 1, 1. There exists an embedding into something that is hyperarithmetic, that's sigma 1, 1. Because hyperarithmetic is also sigma 1, 1. So that's also true for sigma 1, 1 orderings, I guess. It's sigma 1, 1, and it's contained in O because this one is a well ordering, so these are all well orders. So it's contained in O. Sigma 1, 1 and contained in O by sigma 1, 1 bounding. There is a computable ordinal alpha, there is a bound for this E. So that means, what are these guys? Well, these are all the ones that are less than or equal A. So that means that A is less than or equal this bound. And this bound, this is a computable ordinal, and this one is a smaller ordinal, so it must be computable too. Yeah? So that's how you get, that if you have hyperarithmetic well ordering, it's also computable well ordering. This is it's completely different proof, but let me mention it. If you have an infinitary formula that has a hyperarithmetic tree representation, so you can represent it in a hyperarithmetic way, then there is an equivalent formula that is computable infinitary. So that tells you how these hyperarithmetic sets have these very nice closure properties, because I define the hyperarithmetic sets as being the ones definable by computable infinitary formulas. Now I say, okay, what about the sets that are definable by hyperarithmetic infinitary formulas? Well, you still get the hyperarithmetic sets. You get the same sets. So it's like a very nice closure property of the hyperarithmetic sets. They are definable by hyperarithmetic infinitary formulas. Okay, so Spector proved that in 55. This is a result from my... You can go to a bound. You can go recursively to the upper bound. No, you cannot hit it exactly, because you can play with the exact Cantor normal form of the ordinal. You won't get it right computably. So you can code non-computable things into the end of the Cantor normal form, and you won't get it right computably. So you can get an upper bound effectively, but not on the nose. The theorem here is, no, here you get it exactly. Here this proof is, is completely different. It's much more complicated. So here what you do is when you have your representation as a tree of the formula, you have to put it inside a computable tree that is larger. And now you have to prove that every hyperarithmetic, well, you know that for a hyperarithmetic property there is a computable infinitary formula over the empty vocabulary that is true or not, whether this hyperarithmetic fact is true or not. And then you can use that, you have to use those formulas to write down the big formula and say, if this one belongs to the tree and is of the form, it's an infinitary disjunction, then use this and that. If it is a for all, use this and that. So you have to unravel the whole formula. It's going to be higher, yes. Mm-hmm. Okay, so this is a generalization of Spector's theorem that was in my PhD thesis. It says that if you have a hyperarithmetic linear ordering, so now it's a linear ordering hyperarithmetic representation, is bi-embeddable with a computable one. So it's a computable linear ordering that you can embed them back and forth one into the other. This generalizes Spector's theorem because if an ordinal is bi-embeddable with a linear ordering, it must be isomorphic to it. So in the case of ordinals, use isomorphism. But it's true for all linear orderings. And the original proof, don't worry about, I'm just saying that I'm just throwing like the names of things that were necessary in that proof. You have to use Lever's theorem of the quasi-orderings of linear orderings to analyze the structure of all these linear orderings under embeddability, and then produce these invariants, these bi-embeddability invariants that were finite trees with ordinal labels, computable ordinal labels, and then from these invariants, you have to build a computable linear ordering with that invariant. Okay, so there was a lot of work there trying to understand the structure of these linear orderings under embeddability. And so already back then, I guess for the NSF application in, I guess, 2006, I was, okay, so I want to know what's going on, because it sounds like this property, I don't know, it's a very natural property. Something must be going on. So why? Why is that something will have this property? Hyperarithmetic is recursive. What's making the linear orderings have hyperarithmetic is recursive? Okay, well, there was a proof, but it feels like there is something more going on. And then after that, or maybe published at the same time, but it was after that, with Noam Greenberg, we showed that the same is true for abelian torsion groups. If you have an abelian torsion groups that is hyperarithmetic, it's bi-embeddable with a computable one. And for that, you have to use Ohm invariants, and Barwise and Eklof in 71, they produce this bi-embeddability invariants for torsion P groups, depending on the Ohm sequence of the P group. You have to divide your group into the possible P groups, and then you look at the Ohm sequence and define these invariants, and they also are sampled finitary, and then from the invariants, build the tree. You have to also see that hyperarithmetic groups have Ohm rank less than or equal omega 1ck. If it's less than or equal omega 1ck, you get a computable operator. So don't worry about what I want to say. I'm just saying the things that we use. If it has rank equal omega 1ck, you have to look at the divisible part, and that divisible part has to be isomorphic to this, which has a computable copy. It's bi-embeddable with that one. So that was the proof, using like the structure of these groups. So a completely different proof than the case of linear ordering. So the proof only applies to here. Again, what's going on? So that was 2005. Here is another example. This is from 2012. So, okay, so Voss conjecture says that if you have an L omega 1 omega infinitary sentence, that's like the ones that we were looking at, it either has countably many or continue many countable models. I want to say that a sentence is a counterexample if it doesn't satisfy that. I wanted to say this. Don't worry about it. I'm going to repeat this. I'm going to explain this better in a future slide. So a counterexample is a sentence that has uncountably many models, but not continuum many models. Just not to have to deal with continuing hypothesis, I say perfectly many models, a perfect set of models. And in so 2012, the theorem was that if you have a sentence that has uncountably many models, then the following are equivalent. One that is a counterexample to Bose conjecture, and the other one is that every hyperarithmetic model of T is isomorphic to a computable one relative to some oracle. So the relative to some oracle is important to make the theorem true, though morally it's not that important. It's still, because, yeah, I'm sure if you find a counterexample, this is going to be true without the oracle. But so in a sense, it's another example of hyperarithmetic is recursive. So if you have a hyperarithmetic model of T, it's isomorphic to a computable one. Well, I mean, it's another example of this property if we had a counterexample to Bose conjecture. Bose conjecture is open. We don't know if a counterexample exists. If it exists, it will be. Okay, relative to, I'm going to skip that. Okay, so this property keeps on popping up. So let's generalize the property. Or the notion. So you have an equivalence relation E on the reals, which say that it satisfies hyperarithmetic is recursive if every hyperarithmetic real is E equivalent to a computable one. Okay? So you have an equivalence class satisfies that every hyperarithmetic real is E equivalent to a computable one. Equivalence relation. Yeah, really, that's what I meant. Yes, thanks. So it's an equivalence relation E. And I'm saying each equivalence class of hyperarithmetic real has a computable member. So all the examples that I mentioned before are examples of these. So isomorphisms of well orderings, that's Spector's theorem, bi-embeddability on linear orderings, bi-embeddability on torsion abelian groups, isomorphisms of models of a counterexamples to Bose conjecture, if they exist, well, relativized. So those are examples of this property. Here's another example. X and y are equivalent if and only if omega 1x is the same as omega 1y. So the same thing as saying they compute the same ordinals. The class of ordinals they compute are the same. That also satisfies hyperarithmetic is recursive. Those are pretty much the examples that I know, the natural ones. All of these ones are sigma 1, 1. All of those equivalence relations. In some cases, you might say, well, look at this is only works on well orderings. But what we can do is on all the reals that are not, or we're not considered, just make them equivalent to each other and just make one equivalence class with all the other ones. And it's still sigma 1, and it still satisfies hyperarithmetic is recursive. Okay, one more definition. I would say that A satisfies hyperarithmetic is recursive trivially if every real is equivalent to a computable one. Okay, that's very tricky. I don't know if you have isomorphisms on vector spaces. The vector spaces are only finite dimension or Q vector spaces. There are only countably many of them. There are computable copies of all of them. This trivially satisfies hyperarithmetic is recursive. Okay, so the question keeps now is what makes an equivalence relation satisfy this property? And I'm going to give you the answer in the next on Thursday. Okay, so before that, we have to be careful with the question because you can build odd examples. For instance, if you have an E is an equivalence relation that is sigma 1, you can define a new one that does the following. Two things are equivalent if they are equivalent using E, or omega 1 is equal to omega 1 ck. So for the things with omega 1 equal to omega 1 ck, we make them all equivalent. In the rest, we use E. And then, well, if this is not an equivalence relation, you take a transitive closure. It satisfies hyperarithmetic is recursive because all the hyperarithmetic sets satisfy this property, and they are all equivalent, and they are all equivalent to the recursive ones, and we are not using E at all. So we just changed it a little bit on the hyperarithmetic set, and we make it satisfy hyperarithmetic is recursive. But this is a trick. No, we're not going to find a characterization of hyperarithmetic is recursive if we're allowing to use that. So the right question is, what makes an equivalence relation satisfy hyperarithmetic recursive relative to every oracle on a coin? Okay, I think I'm gonna stop. I'm gonna stop there, and we'll continue on Thursday. Any questions? Okay. Yeah, no, I wouldn't know, I guess. Yeah, we have to use the determinacy and. Okay, so next time we'll finish this part. So that's gonna be it's not like that basic. Then we go to overspill arguments. That's a section that is back to the 60s. I explain a technique that is very useful in this area. And then we go to an application of jump hierarchies and overspill arguments in computable structure theory for the fourth lecture. All right, thank you.